So on Wednesday last week, we looked at two very important classes of groups, matrix groups and permutation groups. Let me just say a couple of words about them as kind of review, if you like. So you have to know how to multiply 2x2 matrices. And it's row into column is the rule. So AE plus BG. So you can think of as 2x2 matrix has 2 rows and 2 columns. There are 4 positions that have to be filled in, 4 coordinates. AF plus BH, CE plus DG, and CF plus DH. So it's hard to remember these different letters, but it's easy to remember. It's always row into column. So the ijth coordinate, and in a matrix, the first coordinate always means the row. This is row I. And the jth coordinate always means the column. So that's column J, is sort of the product of row I and column J. Sort of like the dot product that you saw if you saw calculus 3. So if you have 2, 7, minus 1, 4, and 8, 0, 3, minus 9, when you multiply them, you get 2 times 8 is 16 plus 21. 2 times 0 minus 63 minus 8 plus 12 minus 36. So you should be able to do this because this, if there were a question like this on the midterm, this would absolutely be the easiest question on the midterm. So maybe it's an exercise for you right now. Multiply these 2 matrices and tell me what you get. You have to calculate 4 numbers. So what is in the first row, first column coordinate? You take the first row and the first column on the right. And when you multiply them, you get 5 times 1 plus minus 2 times minus 2, which is 5 plus 4, which is 9. 5 plus 4 is 9. What is the coordinate in the first row, second column? Can someone tell me?
Five minus 2.
Well, 5 minus 2 is the first row, but this is a number, it's not a row. So what number goes in here? This is first row, second column. Second column is 4, 8. So that's 5 times 4 plus minus 2 times 8. That's 20 minus 16. That's a 4.
Oh, wow. Oh, shit. I can't have 20 minus 16.
What goes in the second row, first column? Minus 3 minus 14, I think, is minus 17. And second row, second column is minus 12 plus 56. 56 minus 12 is 44. So this is the product of these two matrices. And what is true about matrix multiplication is the following. Matrix multiplication is associative. So if you have matrices A, B, and C, 2 by 2 matrices, you can multiply AB and then multiply that by C, and that's the same as multiplying A by BC. We have an identity matrix, I, which is 1, 0, 0, 1. That's the identity matrix. And I times A is A for every matrix A, and A times I is A for every matrix A. That's why it's called the identity. It's just like the number 1 for multiplication, only this is for matrix multiplication. And if A is A, B, C, D, the determinant of A, which is usually written DET of A, this is you take the diagonal elements AD, the opposite diagonal elements BC, and you subtract them. So the determinant of a matrix is AD minus BC. So for example, for the matrix we saw before, if A is minus 5, 2, 3, 7, the determinant of this matrix is AD minus 5 times 7 minus BC, 2 times 3, that's minus 35 minus 6 is minus 41. If we took the matrix, let's say B, to be minus 5, 2, minus 3, 1, the determinant of the matrix B would be diagonal elements, minus 5 times 1, minus the sort of off diagonal elements, 2 times minus 3. That's minus 5 plus 6, or 1. So this matrix has determinant 1. Suppose I take the matrix C to be equal to 5, 3, 3, 2. The determinant of C is 5 times 2 minus 3 times 3. That's 10 minus 9. That's also 1. Any questions about this? These are not proofs in any sense. These are just calculations. And sometimes people say, oh, I wish I had more calculations than proofs. So these are calculations. Let's multiply the matrices B and C together, see what we get. So B times C, that's the matrix minus 5, 2, minus 3, 1, times C, that's the matrix 5, 3, 3, 2. When you multiply that, it's sort of, again, row into column, minus 25 plus 6 is minus 19. Minus 15 plus 4 is minus 11. Minus 15 plus 3 is minus 12. Minus 9 plus 2 is minus 7. That seems to be the product. what is the determinant of BC? It's minus 19 times minus 7 times minus 11 times minus 12. Let's see, minus signs cancel. That's 7 times 19 minus 11 times 12. Let's see, 7 times 19, 7 nines are 63. 7 plus 6 is 13. 11 times 12 is 32. It's 1. So the determinant of BC is equal to 1. And you remember when we calculated the determinants of B and C separately, they were each equal to 1. So in this example, the determinant of BC is the product of the determinants of B and C. And that's another basic fact about matrices. For 2 by 2 matrices, A and B, it's always the case that the determinant of the product of the matrices is the product of the determinants. Now, we saw with 2 by 2 matrices that there's a multiplication, matrix multiplication, that's associative, and there's an identity element, which is the identity matrix. If A is A, B, C, D, and the determinant of A, which is AD minus BC, is 1, that was the case with these 3 examples, then A has an inverse. A is invertible. And A inverse is the following matrix, D minus B minus CA. Okay. How do I know that? Well, I know it because someone worked this out 100 or 200 years ago, and you have to remember it. Just like you have to remember the times table. But let's just check. A times this matrix, which I called A inverse, this is A, B, C, D, times D minus B minus CA. When I multiply these 2 matrices, I get AD minus BC minus AB plus AB, CD minus CD minus BC plus AD. These 2 coordinates are 1, if the determinant is 1. And CD minus CD is 0, and AB minus AB is 0. This is the identity. And you can check that A inverse times A is also the identity. So as I explained last Wednesday, and this is again just a kind of review, if SL2Z, that's sort of a strange notation, but this means all matrices A, B, C, D, where A, B, C, D are integers, and the determinant AD minus BC equals 1. This is a multiplicative, because the matrix, the group operation is matrix multiplication, is a multiplicative group. And if you take almost any 2 random examples, you should see that this group is not abelian. For example, a moment ago, I calculated the product of the matrices B and C, where B was minus 5, 2 and minus 3, 1, and C was 5, 3, 3, 2. And when I calculated them, I got that BC was equal to minus 19 minus 11 minus 12 minus 7. Now what happens if I multiply in the opposite order, C times B? C is 5, 3, 3, 2. B is minus 5, 2, minus 3, 1. When I multiply these, I get minus 25 minus 9, that's minus 34. 10 plus 3 is 13. Minus 15 minus 6 is minus 21. 6 plus 2 is 8. So that's CB. And when I compare these two, I notice, this is important, BC is not equal to CB. So this group is non-abelian. It is not commutative. Okay. Any questions about this? Suppose I let H be the set of all matrices of the form 1, n, 0, 1, where n is in Z. So you have the matrix when n is 0, 1, 0, 0, 1. When n is 1, you have 1, 1, 0, 1. When n is 2, you have 1, 2, 0, 1, and so forth. When n is minus 1, you have 1, minus 1, 0, 1, and 1, minus 2, 0, 1, and so forth, right? This is some infinite set of matrices, and the determinant of the matrix 1, n, 0, 1 is 1 times 1 minus n times 0 is 1. So every one of these matrices has determinant 1, and H is a subset of SL2Z. Because every element of H is an integer, is a matrix, a 2 by 2 matrix whose coordinates are integers, and the determinant is 1. Any questions about that? So let's look at this set of matrices H in a little bit more detail. So again, H is the set of all matrices 1, n, 0, 1, where n is an integer. What happens if I multiply two such matrices? So suppose I take 1, m, 0, 1, and 1, n, 0, 1. When I do matrix multiplication, I get 1 plus 0 is 1. 0 plus 0 is 0. What goes down here? 0 plus 1 is 1. But what's in the upper right-hand corner? First row, second column, n plus m. You get exactly this. So for example, if I let A sub k be the matrix, or A sub n, be the matrix 1, n, 0, 1, what this identity says is that AM times AN is A m plus n. So there's this nice multiplication rule. So what this says, among other things, is that H is closed under matrix multiplication. And so I take any two matrices in the set H and I multiply them, I get another matrix in the set H. And the identity matrix, 1, 0, 0, 1, that's just A0. That's this matrix when n is 0. So this is an H. And what is the inverse of the matrix AN? It's 1 minus n, 0, 1. Because if you take an times an inverse, which is the same as a sub minus n, that's an minus n, or a0, or the identity. In other words, I take 1 n0, 1, and 1 minus n0, 1, and I multiply them. The n cancels the minus n, I get the identity. So H is a subgroup of SL2Z. A subgroup of a group is a subset that contains the identity of the group, is closed under multiplication, and contains the inverse of each of its elements. Any questions about that? In some sense, even though this is a multiplicative group of matrices, the subgroup H somehow looks like the integers from this rule. And in fact, we can say the following. So we have Z, which is 0, plus minus 1, plus minus 2, and so forth. This is the additive group of integers. And I have H, which is all matrices 1 and 0, 1, which is a multiplicative group and a subgroup of SL2Z. I can define a function f from Z to H by f of the integer n is the matrix 1 n 0 1. So this is a function that associates to every integer this matrix. And if I take any integers, m and n, positive, negative, or 0, f of m is a matrix, f of n is a matrix, I can multiply them. F of m is 1m0, 1, f of n is 1n0, 1. When I multiply them, I get 1 m plus n 0, 1. That's equal to f of m plus n. So this function from this group to this group has the property that f of m plus n is f of m times f of n. So if I take two elements of the integers, I can add them in G and then apply in Z and then apply the function f. Or I can apply the function f first and get two matrices and multiply them in H. But I have this sort of functional equation. What else can we say about f? F is 1 to 1, because every integer n gets mapped to a unique matrix in H, and onto, because every matrix in H is of this form, so it's f of n for some integer n. So f is a 1-to-1 correspondence. And this is an example of what is called an isomorphism. So that G and G prime be groups, we say G is isomorphic to G prime. And the notation is this sort of congruence symbol from geometry. If there exists a function f from G to G prime that is 1-to-1 and onto, and satisfies f of, if I take two elements, x and y in G, x times y in G is f of x times f of y in G prime, where these dots mean the binary operation in the appropriate group. So for example, if G is the integers, this would be addition. If G prime is matrices, this is matrix multiplication. So I just showed that for this group H of matrices, Z is isomorphic to H. This is our first example of isomorphism, which is a fundamental concept all through mathematics. Okay. So up until the definition of isomorphism, this was a review of what I did on Wednesday. And the new concept introduced just now is that of an isomorphism between groups. And we'll have much more to say about this later in the next few weeks, but it's important to get to see examples of isomorphism early on so you begin to develop an understanding of them. All right. Any questions about this? Okay. Now let's continue our review. The other set of groups we talked about on Wednesday last week was the set of permutation groups. And the simplest or the most fundamental are the so-called symmetric groups. So the symmetric group Sn is the group of permutations of the finite set of integers 1, 2, 3, up to n, for every positive integer n. And remember, a permutation of any set x is a function, I'll denote it by the Greek letter sigma, from x to x, that is a 1-to-1 correspondence. That is a 1-to-1 and onto function. And the standard representation of sigma in Sn is sigma equals, and you write this as a matrix with 2 rows and n columns. The first row is just all the numbers from 1 up to n, and sigma is a function from the set 1 to n to itself. So sigma of 1 is an integer, sigma of 2 is an integer, up to sigma of n. You just put, this sends k, and what's underneath it is sigma of k for every k. So for example, if n is 4, suppose sigma is the permutation given in standard representation like this. So what does this mean? This means that sigma of 1 is equal to 3. Sigma of 2 is equal to 1. Sigma of 3 is equal to 4. Sigma of 4 is equal to 2. So this is the one-to-one and onto function from the set 1, 2, 3, 4 to itself. Defined this way. If we had another permutation, maybe 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 4, that's another permutation in S4. And it's very important to understand these are functions. So you want to compute sigma tau. Multiplication of permutations is composition of functions. Sigma tau is, this product is composition of functions. So how do you compose functions? You want to know what is sigma tau of 1. That means sigma of tau of 1. Tau of 1 is equal to 2. So this is sigma of 2. Sigma of 2 is 1. So sigma tau of 1 is 1. What is sigma tau of 2? It's sigma of tau of 2. Tau of 2 is 3. So this is sigma of 3. Sigma of 3 is 4. What is sigma tau of 3? That's sigma of tau of 3. Tau of 3 is 1, so that's sigma of 1. Sigma of 1 is 3. So sigma tau of 3 is 3. What is sigma tau of 4? That's sigma of tau of 4. Tau of 4 is 4, so that's sigma of 4. Sigma of 4 is 2. So let me write this down again so it doesn't get lost for the moment. So I have sigma is the permutation 3142 in S4. Tau is the permutation 2314 in S4. I calculated sigma tau. Sigma tau sends 1 to 1, 2 to 4, 3 to 3, and 4 to 2. So it's this permutation in S4. Suppose I multiply sigma tau in the opposite order. What is tau sigma going to be? Let me calculate. Tau sigma of 1 is tau sigma of 1. Sigma of 1 is 3. That's tau of 3. Tau of 3 is 1. So tau sigma of 1 is 1. What is tau sigma of 2? Tau sigma of 2. Sigma of 2 is 1, so this is tau of 1. Tau of 1 is 2. What is tau sigma of 3? That's tau of sigma of 3. Sigma of 3 is 4, so this is tau of 4. Tau of 4 is 4. So tau sigma of 3 is 4. I have to double check. I'm not sure everything is correct. But tau sigma of 4 is tau of sigma of 4. Sigma of 4 is 2. So this is tau of 2. Tau of 2 is 3. So this says tau of 1 is 1, tau of 2 is 2, tau of 3 is 4, and tau of 4 is 3. So if I compare these two, sigma tau is the permutation 1, 4, 3, 2. Tau sigma is the permutation 1, 2, 4, 3. These are different. Sigma tau is not the same as tau sigma. So S4 is not abelian. It is a non-abelian group. So let's pause for a minute. So you might want to double check this calculation. Just go through and check all the numbers, make sure it's legit. Any questions about this? How the calculation goes? Okay. So a particular kind of permutation is called a cycle, or may call it a case cycle, is a permutation sigma in Sn of the following form. We write it as in one line, A1, A2, A3 up to A sub k, where A1 up to A sub k are distinct numbers in the set from 1 to n. And we think of the cycle, the permutation, as being of the following sort. A1 goes to A2. A2 is sent to A3. A3 is sent to A4. A4 is sent to A5, and so forth. A sub k minus 1 is sent to A sub k, and A sub k is sent back to 1 by sigma. And so sigma of AI is AI plus 1 for I going from 1 up to k minus 1. Sigma of AK is sent back to A1, and sigma of A is equal to A for all A different from the AIs. So for example, suppose we consider the cycle 1, 2, 3 in S5. So our little picture in this case, 1, 2, 3, 1 goes to 2, 2 goes to 3, 3 goes back to 1. What's left in S5? 4 goes to 4 and 5 goes to 5. So this permutation 1, 2, 3, if we write it in standard form, 1 goes to 2, 2 goes to 3, 3 goes back to 1, 4 stays at 4, and 5 stays at 5. So sigma is a 3 cycle. It moves 3 elements around in a circle and keeps everything else unchanged. And one of the theorems about permutations that I explained last week is the following. Every permutation is a product of disjoint cycles. So let's look at an example. Let's make it interesting. So suppose I take sigma there we go. That's about as far as I can get. So this is going to be a permutation of the numbers 1 to 13. Let's see, I haven't used 3 yet. I haven't used 4 yet. I haven't used 6 yet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a permutation in S13. And the way you write this as a product of disjoint cycles is take any number to start with. I'll start with 1, but I don't have to. Let's just follow 1 as we iterate this permutation sigma, as we compose this function with itself. 1 gets sent to 9. 9 gets sent back to 1. Okay, that's what it is. Let's take the next number that hasn't occurred yet, 2. 2 gets sent to 13. 13 goes to 4. 4 goes to 7. 7 goes to 10. 10 goes to 6. 6 goes to 12. 12 goes to 11. 11 goes to 3. And 3 goes back to 2. So I have the 2 cycle 1, 9. And I have this 11 cycle 2, 13, 4, 7, 10, 6, 12, 11, 3. And sigma is the product of this 2 cycle and this 11 cycle. This sends 1 to 1 and 9 to 9. So under composition of functions, 1 goes to 1 goes to 9. 9 goes to 9 goes to 1, and so forth. 2 goes to 13, stays at 13. So just to see if you can do these kinds of calculations, suppose I take another permutation.
Professor,
Yeah,
isn't it 9 cycle instead of 11 cycle?
1, 2, 3, 4, 5, 6, 7, 8, 9. So what did I leave out? 2, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, thank you. Very good. That means
We missed the
must be some numbers that are missing. What's missing?
5.
5 goes to 5 times 5, 8. Thank you. So this permutation sigma is a product of a 2 cycle, a 9 cycle, and another 2 cycle. Thank you. Because these numbers have to add up to 13. I'm just sort of putting numbers down more or less at random. See what's missing. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I used 7 twice. That's not good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Make this 13 and this 11. Okay. So this is another permutation in S13. And let me write this as a product of cycles. So 1 goes to 6, 6 goes to 10, 10 goes to 9, 9 goes to 4, goes back to 1. So that's a 5 cycle. 2 goes to 7, goes back to 2. That's a 2 cycle. 3 goes to 5, 5 goes to 13, 13 goes to 11, and 11 goes back to 3. That's a 4 cycle. What haven't I used yet? 8. 8 goes to 12, and 12 goes back to 8. So tau is a product of a 5 cycle, a 2 cycle, a 4 cycle, and a 2 cycle. And notice these cycles are pairwise disjoint. These numbers are different from these, or different from these, or different from these. And every number pops up one time and only one time. So this is the cycle decomposition of a permutation. Okay. And I should add the fact, it's also a theorem, disjoint cycles commute. So if you have a K cycle and an L cycle, and AI is different from BJ for all I and J, so none of these numbers is equal to one of these numbers, and conversely, then you can write this in the opposite order, and these are the same permutations. So disjoint cycles commute. The simplest cycle is a 2 cycle, which is called a transposition. So for example, here, where I decompose tau, I had a 5 cycle, a 2 cycle, a 4 cycle, and a 2 cycle. this and this, these were transpositions. They're just the shortest possible cycles. And all a transposition does is interchange two numbers. So if sigma is equal to AB in Sn, that means if you write sigma in a standard form, all the numbers stay in the same place, except A and B. A goes to B and B goes to A. This is a transposition. Sometimes you like to think of a transposition, a permutation as being just arrangement of numbers, like 3, 2, 5, 4, 1 is a permutation of 1, 2, 3 up to 5. So if I took 1, 2, 4, 3, 5, this is the permutation with 3 and 4 interchanged or transposed. But again, we always think of this as sigma in standard form, 1, 2, 3, 4, 5, 1, 2, 4, 3, 5. So sigma of 1 is 1, sigma of 2 is 2, sigma of 5 is 5, but sigma of 3 is 4, and sigma of 4 is 3. Right, that's the transposition. And we know that every permutation is a product of disjoint cycles, but it's also true that every cycle is a product of transpositions. But it's important to say this is always true in at least one way, but not disjoint transpositions. And not in a unique way, not uniquely. So for example, suppose I take sigma to be the permutation in standard form, 1 goes to 2, 2 goes to 3, 3 goes to 1. But this is just a 3 cycle, 1, 2, 3. I claim this is a product of transpositions. In fact, I claim this is the product of 1, 2, and 2, 3. So this 3 cycle is a product of 2 transpositions. Let's just double check. You have to really, this is composition of functions. So 1, 2, 3 sends 1 to 1, and 1, 2 sends 1 to 2. 2, 3 sends 2 to 3, 1, 2 sends 2 to 1. Two, 3 sends 3 to 2. Oops. Sorry, I made a mistake here. 2 goes to 3 and 3 goes to 3. 2, 3 sends 2 to 3, 1, 2 doesn't move 3, so 3 goes to 3. 2, 3 sends 3 to 2, and 1, 2 sends 2 to 1. So this is the cycle. 1 goes to 2, 2 goes to 3, 3 goes back to 1. So that's a proof of this identity. The general important fact, an important fact about permutations is the following. Suppose I let A1 up to A sub L be L distinct integers in the set from 1 to n. If I take the K cycle, A1, A2 up to A sub K, this is a K cycle. And if I take the numbers AK plus 1 up to A sub L, so this is an L minus K plus 1 cycle. So I have a K cycle, an L minus K plus 1 cycle. If I multiply these permutations, I get this L cycle. So this is a very general, simple fact about permutations, but it's used a lot. Why is that? Because if I look at this, A1 goes to A1 goes to A2, A2 goes to A3, A sub K minus 1 goes to A sub K, AK goes to AK plus 1, and so forth. AL goes back to AK, and AK goes back to A1, so AL goes back to A1. So if you look at this element by element, you see exactly this decomposition. But the only way to understand this is to write down examples and calculate them for an hour or so. So let's look at an example of this. So this is the statement. If I have a K cycle followed by an L minus K plus 1 cycle, and all the numbers are different except the last one on the left is the first one on the right, I get this. So for example, 1, 2, 3, 4, 4, 5, 6 should be 1, 2, 3, 4, 5, 6. You just concatenate these and run them together. So this says 1 to 1 to 2, 2 to 2 to 3, 3 to 3 to 4, 4 to 5 to 5, 5 to 6 to 6, 6 to 4 back to 1. Yeah. And the numbers don't have to be consecutive. 2, 7, 3, and 3, 11, 5. This is the cycle that sends 2 to 7, 7 to 3, 3 to 11, 11 to 5, 5 to 3 back to 2. You concatenate them, just overlapping the 3s. 2, 7, 3, 3, 11, 5. One property of the K cycle is the following. For example, if I take 2, 3 times 2, 3, so I take this transposition and multiply it by itself, I get 2 goes to 3, goes to 2. 3 goes to 2, goes to 3. This is just the identity, E. In fact, for any K cycle, sigma to the kth power is the identity. And if you think of a K cycle geometrically, A1 goes to A2, goes to A3, goes to A4, to A sub k back to A1. If you do this cycle once, A1 goes to A2. If you do it twice, A1 goes to A2, goes to A3. If you do it 3 times, A1 goes to A4. If you iterate this or compose this cycle with itself, k minus 1 times, A1 goes to AK. If you go k times around, every number comes back to itself. That's why sigma to the k is the identity. So that's a kind of a nice geometrical proof of this phenomenon. Okay. All right, so when you're studying groups, it's important to have examples, and permutation groups and matrix groups are nice examples of non-abelian groups. For abelian groups, a very important example is what is called a cyclic group. So suppose we take some variable or symbol, let's say A. What is the cyclic group of order n? You have an identity in element A. You just start multiplying A by itself. And I'll call this gamma sub n. And A to the n is the identity. So you just have a set of these n symbols, E and then the powers of A up to A to the n minus 1, with the rule that A to the n equals the identity. And you can multiply A to the I times A to the j. This is going to be A to the I plus j. At least if, so 0 and I and j are between. Let me say that A to the 0 is the identity. That's just that we define the 0th power of an element to be 1 of the identity. So for ij, between 0 and n minus 1, A to the I times A to the j is A to the I plus j if I plus j is less than n, less than or equal to n minus 1. And A to the I plus j minus n if I plus j is greater than or equal to n. So for example, what is the cyclic group with 5 elements? It's, well, I'll make it 4 elements. It's EA, A squared, and A cubed. So for example, A means A to the first power, of course. So A times A squared is A to the 1 plus 2, or A cubed. A squared plus A cubed times A cubed, that would be A to the 2 plus 3 power. But 5 is bigger than 4, so you have to subtract 4. So that's A to the first power. Or if you like, A squared times A cubed is A to the 5th, but A to the 5th is A to the 4th times A. And in a cyclic group of order 4, A to the 4th is the identity. So this is just the identity times A, or A. It's exactly the same thing. Now we can write down the multiplication table for this group. So I have EA, A squared, and A cubed, EA, A squared, and A cubed. When I multiply, the identity times any element is the same element. And any element times the identity is that element. A times A is A squared. A times A cubed, A times A squared is A cubed. A times A cubed is A to the 4th power, which is the identity. A squared times A is A cubed. A squared times A squared is A to the 4th power, which is the identity. A squared times A cubed is A to the 5th, which is A. A cubed times A is A to the fourth is the identity. A cubed times A squared is A to the fifth, which is A. A cubed times A cubed is A to the sixth, which is A to the fourth times A squared, which is the identity times A squared, which is the identity. So this is the multiplication table for gamma to the fourth. Now, if you look at this, you might notice something interesting. This looks like the addition table for the integers mod 4. The congruence class is mod 4. If you look at the congruence classes mod 4, the representatives are 0, 1, 2, and 3. When we add mod 4, this is what we get. And it's exactly as if here I have elements in this group, the cyclic group with 4 elements. Here I have congruence classes in the integers mod 4. It's sort of like you take the exponents and just write them, you get the same thing. So that actually is a very interesting observation. And in fact, we can prove from this, in general, the following. The multiplicative cyclic group gamma M is isomorphic to the additive group Z sub M, or Z mod MZ, your choice of notation, of congruence classes modulo M. And the proof is we can define a function from the congruence classes mod M to the cyclic group of order M by f of, let's say, the integer k, the congruence class, f of k plus mz is equal to a to the k. And you can check what is f of the sum of 2 congruence classes. That's f of the congruence class k plus l plus mz. That's equal to a to the k plus l, which is a to the k times a to the l, which is f of k plus mc, that's a to the k, times f of l plus mc. And you can check that this function is 1-to-1 and onto. What's another example of a cyclic group of order 4? So I take a cyclic group of order 2. Suppose I take G to be the numbers 1 and -1 under multiplication. So this is like EA, where E is 1, A is -1, and A squared, which is -1 times -1, is +1, which is E. This is a cyclic group with two elements. This G is isomorphic to gamma 2. So if you just think of the numbers 1 and -1, that's an example of a cyclic group of order 2. We can use complex numbers to construct a nice example of a cyclic group of order 4. So in the complex plane, here's the unit circle. This is the number 1, I, -1, minus I. So as I take G to be these four complex numbers, 1, -1, I, minus I. So 1 is I to the 0. I squared is -1. I cubed is I squared times I, which is minus I. I to the 4th is I squared times I squared, which is -1 times -1, which is +1. So this is the cyclic group of order 4 generated by I. Okay. If gamma n is EA squared up to a to the n -1, this is a cyclic group of order n, then A is called a generator of gamma n. You can use any symbol for A, B, C, X, or in this case, even the number I, the complex number I. So a cyclic group of order n generated by A is all powers of A with the constraint that a to the n brings you back to the identity. And if I take these four complex numbers on the unit circle, +-1, +-I, they form a cyclic group of order n. This G is 1 I squared, I cubed, which in order is 1 I -1 minus I. Any questions about this? If you play a little bit more with complex numbers, if you take the unit circle and you construct the equilateral triangle with a vertex at 1, this point is -1/2 plus √3/2I. And this is -1/2 minus √3/2I. Let's call this number rho. And this number is rho squared. And if I take G to be 1 rho and rho squared, these three complex numbers, this is a cyclic group of order 3. Because rho cubed, if you just take rho and cube it, rho cubed is right there. Any questions about this? So I've spent 2 whole days now just talking about the matrix groups and the permutation groups and now these cyclic groups, because these are very concrete examples of groups, and you can't do a subject in abstract algebra. If it's so abstract, you don't have examples. You need to have examples that you understand, that you work with. And before class, I posted some lecture notes on matrix groups and permutation groups. And I assigned some homework for Friday involving these groups, all three of the groups I talked about today, cyclic groups as well as matrix groups and permutation groups. And the more exercises you can do and the more time you can spend trying to do these calculations, the stronger will be your knowledge of algebra. Okay. Any questions about any of this? I'll post some office hours later today. So I have these problem sessions when I'm online, and I encourage you to take advantage of them. Ask questions. Because you learn a lot by asking questions and seeing what the answers look like. All right, if there's nothing else, we will take a break. It's going to be warm today, so enjoy the day if you can. All right, all. Next class, next lecture is on Wednesday. This is lecture 12, so we're actually approaching the halfway point in the semester. Right? Semester is 28 classes, so this is class 12. Okay, everyone, no questions? We're done for the morning. Bye.